So here's an example of linear programming in terms of a word problem. So it says your club plans to raise money by selling 2 sizes of fruit baskets. The plan is to buy small baskets for $10 and sell them for $15. Buy large baskets for $15 and sell them for $24. The club president estimates that you will not sell more than 100 baskets. Your club can afford to spend up to $1,200 to buy baskets. Find the number of small and large baskets that you should buy to maximize the profit. So what we have to find is a couple different things. We have to find our constraints. And we have to find our objective function. Okay, so when we are looking at this, it's saying that we're going to buy the small ones for $10 and we're going to sell them for $5. We're going to buy the large baskets for $15 and we're going to sell them for $24. Your objective function is talking about what you're wanting to happen. We're wanting to maximize our profit. So we're going to say P equals, so we're trying to maximize this profit. For every small basket, we're going to make $5. So we're going to let X be the number of small baskets. We're going to let Y be the number of large baskets. So we are going to make $5 for each small one. So our profit is $5 for every small basket. Plus, we're going to make $9 for every large basket. So that's our objective function. That's what we're trying to find. Now we have to determine our constraints. Well, it says I can only afford to pay for $1,200 worth of baskets. So I'm buying them for $10 and $15. So I would say 10x, so that's the cost that I would have for the small baskets, plus 15y, which is your cost for your large baskets, has to be less than or equal to $1,200. So I can spend less than or equal to that. Can't spend any more than that. It also says that I will not sell more than 100. So in that case, the number of baskets, so X plus Y, has to be less than or equal to 100. Two other constraints that you always have, or almost always have, are X has to be greater than or equal to 0, and Y has to be greater than or equal to 0. We cannot sell a negative number of baskets. So that constraint is there. So we have all of our constraints. We have our objective function. The next thing we have to do is we have to graph these constraints to form what we call our feasible region. Okay. So we're going to go down and I'm going to show you what the graph would look like. So here's kind of what we just talked about. Here's all of our constraints. Here is our objective function. So what they did is they graphed, notice in red, you see X plus Y is less than or equal to 100. So we'd have to be below the red line that's graphed. And we're also below the blue line that's graphed, which is your 10X plus 15Y is less than or equal to 1200. So the shaded region that you see here is what's called the feasibility region, or the feasible region. Now, notice that we are only using the first quadrant, and that's because of the two constraints at the end, that X and Y both have to be greater than or equal to 0. So that means we are in the first quadrant. Now, what we need to find is what's called the vertices. So those are your intersection points. So, or the outside points. So you have a vertex here, you have another one here, another one here, and your last one is here. So what you have to determine is which one of those points, because one of them will produce the maximum profit. So what you're going to do is you're going to find those points. So notice here that I found the coordinates of X and Y. Remember that X is your small and Y is your large baskets. So you're going to find those points, and then you have to plug those points into your objective function. So for instance, then you would kind of create a little table here, or look at this. So you're going to plug in 0 and 80. So they plugged in 0 for the X, 80 for the Y, and they came up with a maximum profit here, or a profit of 720. You're going to do that with each one to determine which one is maximizing your function. In the other case, if you had a problem that wanted to minimize, you might do that. But that in this case is not what we are looking for. So really what your process is you have to come up with your objective function. You have to come up with your constraints. You have to graph them and find the vertices of the feasible region. And then you're going to plug those vertices in to your objective function to determine which one either maximizes or minimizes your function, depending on what you are trying to find. I hope this helps answer your question. If not, just let me know and we will try something different. Have a good day.